Okay, so let's start the second part of the Arduino, which is about timers and counters. And actually, well, let's start for the timers. In general, timer is an internal peripheral, meaning that it's on the same silicon chip as the processor core itself, directly attached on a internal uh, the internally with the processor. The timer is an internal peripheral that counts. Duh. What does it actually timer count? It counts the how many clock cycles it has actually encountered. So timer actually is just a counter that counts time. The clock signal varies from basically from processor to processor how you can actually feed different clocks and also the programming environment. But in general, the clock signal is fed to the timer, and that's usually derived from the main clock signal. There are some processor environments which may have separate clock signals for the CPU and peripherals, or CPU and memory may have different clocks on bigger systems, but usually it's also that for real-time clock use, there is a possibility to use an external clock input to feed in very precise 32K clock frequency. But anyways, uh, the engineer is the one who is writing applications to control the internal clock signal dividers. So it will be your job, and about half of you will continue on the embedded path. That's the bright side of the force. Sorry, none intended. But anyways, you will be the ones who will be a master of clocks when you take a couple of courses with Keijo and Joe. Timer size depends on the CPU, typically 8 or 16 bits. If there are 8-bit timers, several, then there might be a chance that you can actually cascade timers to make a bigger timers. But actually, it's always a limited numbers. So basically, when the timer reaches the maximum value, it will overflow back to zero. And that's usually something you don't want to do unless you are using the overflow for timing. So keeping that in mind in general, that okay, timer, if you derive from main clock signal and if it's fast enough, you may actually end up in problem by overflowing the timer accidentally. In Arduino environment, I think that's almost impossible. But anyways, on a general the system, that's quite easy to do. On software, the timer actually can be started or stopped, and also the value can be set. So basically, there are some control registers that you write to set up the timer. Okay. All of these timers and counters, they are controlled by special registers. On some CPUs, you can also attach an interrupt to your timer. Practically, I would say all of these processors, you can have a timed interrupt which is pretty handy. That way you can actually do something on, for example, a constant, constantly at the certain rate. For example, you can make A to D converter to sample, say, exactly every 1 millisecond. So taking samples of data once or 1000 samples per second with a constant sampling rate. Okay, that's yes, cron jobs are for yes. Try to make a cron job for 1 millisecond. Good luck with that. Well, 1 millisecond is okay. I'll say 20 microseconds. Yeah, cron jobs in Unix system or Linux systems. Yeah, that's what the cron job does. Yeah, chronological job. Exactly the same thing. Now on a microcontroller. Exactly the same thing. Okay. Interrupt your timer. Yes. Basically, depending on the CPU, it depends how those interrupts are then handled. It can be handled on a count, or it can be actually used for the overflow. Overflow. It depends totally on what kind of processor you're working with. So read that damn manual. That's my advice. Just a moment. Somebody has a. Would you turn off the microphones? There's somebody who has the microphone on. Okay, thank you. This mess here is AVR timer unit internal structure. So inside of Arduino, this AVR processor, and this is how the timer unit looks like internally. Okay. Data bus here is to read and write the register values. Timer / counter, the values can be read or write. Okay, how the timer actually does work. So you have the different places to get the signal, either from IO clock or inside of the processor. There's the timer on counter oscillator, and then we have the well, just a selection. Again, okay, it looks like you must also have some control word for that one, or you need to control some the switches here. There's a prescaling. You also need to set the prescaling for that counter or timer, and that prescaled clock is then fed into the control logic. Wow. Which then controls the counter value itself. So it either counts up or down, or at certain points it can also clear the counter value to start over. Whoa. Lots of things happening on one single thing, one single small part. Okay, there are a couple of the then tests that you can do. Okay, timer counter. You can compare the value with some preset value here. So this timer counter value is controlled by the control logic, and it's counting either up or down, and then you can then compare it with some other value that you can set the reference value. When it's this equal, it gives you a signal that can be used by the control logic. So you can actually make a timer or counter that counts into certain number of counts and then gives an interrupt and starts over. Okay, but there's something like, okay, let's see, there are 7 different registers for each timer what you have here, and on AVR I think there are smaller, I think there are 2 timers, timer 1 and timer 2. So 14 register values to set. Without a nice environment, this would be quite hard. And actually, there's a funny thing about Tinkercad. It does not support timer interrupt as it is. There are actually, if you go to the Arduino documentation, you can find a subroutine library for Arduino for doing it. Unfortunately, you cannot use that on Tinkercad environment since it's limited environment for Arduino. Okay, but anyways, it's not a biggie. I can actually show you how to try the timer, how to set it up. It's not a huge thing actually. You just need to access the registers. All right, so multiple clock sources, prescaler is one. So that's how you select the input timing or input clock for the timer. Then there's control logic. So you can do different things with this timer. For example, setting it up to count for certain amount of clock cycles and give interrupt. Then there's current value of timer is always stored on that register. Then there are, well, not only one comparison, but there are actually 2 compare values that can be used. So there's that OCR A and OCRN B that can be used for comparison. And all of those registers, they are of course software accessible. Okay, just a moment. There's something on chat. Right. So, timer applications. Whether you use timers, well, on these embedded systems, you will use timers. Otherwise, the system doesn't do much of anything. So first of all is keep track of time. Okay, timing can easily generate an interrupt once per second. If you have accurate enough of clock for that one, you will get pretty accurate real-time clocks. Or ensure some functions are executed at fixed time intervals. Or how about making a control that you turn, well, traffic light is a classic example of timer operations, and we are trying to avoid using that one as an exercise since everyone has done traffic lights and those are so darn, say, so useless exercise. I would say that nobody of you will ever need to design a traffic light yourself. Okay, educational, yes, entertaining, not anymore. It was a big thing in 70s and 90s, or 70s, 80s and 90s, but not on this century. Okay, so ensuring some functions are actually at fixed time intervals, for example, that traffic lights turning, keeping it green for a while, then 10 seconds for, or was it 3 seconds for yellow, and then some time for green again. If you want to push the, have this pedestrian button, then it could be interrupt service that changes that somehow. Yeah, it would be entertaining, but not that interesting exercise. And of course, timer applications, you can count occurrences. Yeah, another joke on there. Thanks. Yes, atomic clock. Okay, good luck of interfacing atomic clock with your small processor environment. You don't want to necessarily have a connection for your device. But anyways, yeah, good joke. Atomic clock. Uh, but anyways, timers are needed. Period. Count occurrences. Okay, there is actually a good example of counting occurrences. And I think that was actually the example we were going to show you. Yeah, that was a speedometer for a bike. Fun fact. Ha! This is fun. How any real-time operating or nearly real-time operating system actually work. They have a single processor, although it may have several cores, but it doesn't change the. It gives a little bit more complexity and also more resources to do, but in principle, multitasking is done, is built around timers and interrupts. So the basic flow. Program A is running, then you have a system, the task scheduler that basically multiple sockets are still counted as one processor, yes, and this is actually how you put different sockets to work at the same time, although they are not working at the same time. It just looks that way. So basically you allocate some certain of time for each program by using timer interrupt. So basically timer interrupt occurs and then the handler or the scheduler checks how things are, calculates how long the next execution period should be, which program is turned off for execution, and actually those are set up as parameters for the scheduler. When you make a thread, then you also give it a priority, and based on the priority, the scheduler then gives time for execution. Okay, and then actually scheduler sets a timer according to jumps to the program B or yes. On a place it was interrupted before and actually starts be running, and the schedulers, all of these programs A and B, both of them are thinking that they are running constantly, although the timer interrupt happens and takes the execution to another place, to another program. So they in a program way of thinking, okay, I'm running alone on this computer. No, you are, but scheduler knows the better. It gives some computing time for each of these tasks on a computer. If you have a multi-core system, then you can actually start also shuffling so that there is that one part of the code is, for example, program A is running all the time, and on another core you are scheduling something else. But that goes into a much bigger system now, and now we are talking about operating system level programming. It's fun. I have done it enough. I don't, well, it depends how you define fun. Okay, so yeah, it was fun for a while, although I would say that it's also, yeah, actually the fun part is that it's very challenging. But anyways, yes, there are some details on things that how things are done in certain systems. But again, this is something that you will be, especially those who are going to take the smart systems seriously. Then you will be on your next fall. You will start using FreeRTOS on the ARM processors, and this is one of the things how multitasking is done on FreeRTOS. But anyways, it's really a it's mind-blowing kind of thing to learn how to things are actually working. But for Arduino, we don't have any so-called operating system. It's just that main loop that is computed all the time, and then these interrupt service routines that are interrupting things. So not anything that we could call a real operating system. But multitasking operating system, yeah, it works like that. On Arduino, yes, you can actually build a multitasking operating system. When you just think of this, how to make the timer interrupts work. Okay, so yes, fun fact. This is how operating systems work. Wow. Okay, let's take a look at the standard Arduino functions, but do not provide interface accessing the hardware-based counter timing unit. Oops. Let's open that one and see. Is there anything? Digital I/O, timer counter. Time, only delay, microseconds, milliseconds. So we are more or less. No, we don't have anything standard. We have just the operations, and then some special functions, some variable kind of things special, but nothing on the standard library, which is not a good thing, since actually on that Tinkercad environment we cannot use anything else than what is provided there. Okay, two options. One is add a library written by somebody else that handles the hardware and provides simple to use functions which cannot be used in simulator environment. Okay, this would be the easiest way. So if we had a real hardware, we could easily do that. Okay, but we can still do the homework since we can manage the hardware manually. The device datasheet actually provides detailed information on how the timer unit can be controlled through registers. Okay, there's some light on the end of the tunnel here. There are two 8-bit timers, timer 0 and timer 2, and one 16-bit timer, timer 1. Okay, nice. So now we know, okay, there are these variables Compare registers. Now we know that they are registered for timer 0, 1 and 2. All the timers are managed by number of control registers, and these actually can be found from the MCU datasheet, meaning the AVR datasheet. And okay, let's open that one just for fun. Okay, takes for a while. Done at Mega, and then actually we can find, for example, that one register there. Let's see, there's a TCCR1A. I think this is the easiest way of finding TCCR1A. Okay, registers. So notice anything familiar with this picture? So we have this nice picture what we had also on this our show, and the register looks like that, and then there's the actual definition of different registers and how to access the 16-bit register or 12-bit register with some code examples and everything. So okay, that would be the hard way. We also have actually some, we already have, say, read the data sheet. You don't have to memorize that 400 pages or whatever that was. That was it how many? Oh no, only 300 pages. Okay, one fun fact about embedded systems engineering. It's about reading manuals. Read that F manual. So that's the most common thing what you hear from teachers like Joe and Kay when they are teaching you and you are asking a question that can be from the manual. But actually we are nice. Me and Juho, we are nicer. So we give you some hints before that one. So the fourth timer one, for example, those registers there are 3 control registers, A, B, and C, and then we have timer counters, timer counter registers, high and low, and then there's compare registers, high and low, output compare registers, B, high and low. Okay, remember this is 16-bit counter. The control is 8 bits, so there are 3 control registers, but then the counter itself is 16-bit, meaning it has higher and lower value, the byte. And then it also have interrupt mask register, timer interrupt mask register 1, and then the timer counter interrupt flag register. Okay, and these are you need to set 8 of these registers. And the flag register is something that you can read. It gives information of the state of the counter itself. But those are the registers. It's not that hard anymore, actually. There is some structure. And okay, timer 0 and 2 are exactly like that, different mnemonics, and then it also have it only have 8 bits register for timer counter value and compare value registers. Okay, that's the excerpt. Each of these registers, though, okay, they are, every single bit means something. So you have learned the C programming fundamentals on the last year, I think. Now it's time to start using the bitwise operation, since here you really have to set the bits. Initially, control register for any timer counter, there are zeros, but then you can actually write some of these values. Some of these values, when you write, it does nothing. Basically, it's then only read value. So there we have bit 7, input capture noise canceller. If we have noisy input, turning that off on, it basically removes some of the noise. Then there's input capture edge select. This bit select which edge on the input capture is used to trigger. Okay. Then there's reserved bit. Then there's a 4 bits. Oh, no, sorry. Not 4. 2 bits. Waveform generation mode. So if we are using this timer to generate some waveform, like a PWM or something like that, then you would be using those registers. And then there's a clock select, meaning where to get the this clock. And these are tied into that higher upper right corner. Let's see if it was here. Come on. There on this picture. Here we have a clock select. Where to get the clock. That's the that is controlled by these registers or these bits on the register. So some bits need to be set. So timer clocking. And this is affect how fast the timer is running. Okay. So meaning clock source, prescaling. So yeah, these are the 3 bits. Clock select bit description. So which prescaler are we using? Prescaler meaning just a divider for the clock input. So are we using clock directly? If you use system clock, it's 24 megahertz clock or something like that. Or then you divide by some of those numbers. So in principle, you can make that 24 megahertz clock down to something like 23 point some kilohertz clock if you put the highest prescaler there. Okay. And then some other bits there. So you need to set the bits. Wow. All right. Configuring the interrupt timer. This here, there's a code that sets timer 1 interrupt at 1 hertz. Okay, this is a code segment that you can use as it is. So there's the register, compare registers A and B set to 0, initialize the counter value as 0. By the way, these mnemonics on Arduino are basically reserved for the registers. Then, okay, this is code will set timer 1 to generate compare match type interrupts at the rate of 1 hertz. So if you put this one and then write the interrupt service routine, that should work. Yeah, Arduino. Yes, you can buy Arduino if you are going to the playing with Arduino is not a bad hobby. So, and you can buy these Arduino boards less than 10 euro. Verkkokauppa sells those in 30 bucks, but well, you just walk into Verkkokauppa and buy it. Okay, or buy it from the internet somewhere. There are plenty of both genuine Arduinos and then those which look exactly like Arduinos and work the same as Arduinos, kind of pirate copies for euro or so. So, but anyways, it's up to you if you want to have the hardware or not. I just keeping in mind that okay, you probably will not use the Arduino anymore after this course, except if you're working with the electronics degree program. On electronics degree program, they use those small Arduinos everywhere, or the what is that? The automation technology. They are using Arduinos because they are simple. They do the job, easy to operate. It's a toy, but it's a nice toy, as we said. For the if you are taking this smart systems engineering major, and specialize on the systems or the microcontroller systems, then you will be moving into ARM processors. And they are also, say, cheap ARM processor platforms, so for 10 bucks or so. Okay, but it's up to you. Arduino is a nice toy. I have few of them at home somewhere laying around. I don't do much of them, but sometimes yes, it's fast to test things. Okay, so that code here initializes the registers, sets the compare value for 16-bit register, and then turn on CTC mode. So it's counter mode. That's the bit setting a bit. And then the prescaler bits CS12 and CS10. These actually are giving these reserved mnemonics are giving the position of that control bit on the register. So let's go back a bit. So VGM12 is 3-bit offset on that register. So this one shifts the shifts number 1 on the correct place on that register, and this is OR equals, so that one sets the bit. Okay, and the same thing CS12 and CS10 bits for 1024 prescale, meaning, okay, let's go back. So CS12 is 1 and CS10 is 1 for prescaler of 1024. Okay, and enable timer compare interrupt. That's a timer mask, interrupt mask register. So after that, what you need to do is basically just enable interrupts globally and have an interrupt service routine to do whatever it needs to be done. All right, wow, that was heavy. But fortunately, there are several places you can find some text, some code. And by the way, even if these we cannot download the libraries, we always can set the registers on that environment. So in that sense, we actually can control the timers in Arduino environment. But it means bit bashing. And I think this was a good example. Yes, Arduino timer interrupt. I actually recommend you to read this. Whoops. Oh, what happened? Of course, it opens up a. When you click something, it starts opening. Oh shit. Oh. Okay, I got some funny. I think it's a some sort of funny thing from the internet. Let's see if I can get something else from another example. There was a okay. This is also nice. It also explains how things are done. Okay, and basically some examples there. And yes, there is also it's also how to set up things. So there is a okay. Maybe we can actually copy that one and see what it actually does. So there's the setup section for setting up a timer interrupt. And okay. So setting up timer interrupt for 2 kilohertz timer, or there's interrupt for 1 hertz timer. Okay, that might be handy. Then there's also a timer 2 is for interrupt of 8 kilohertz timer. Depending on the application, I think these are pretty good examples how to set up the start timer routines. I have no idea what does it actually do with if you have also the delay function, since that one is also using the timer. So you might actually use either the delay or make your own delay using your own timer. Uh, in interrupt service routine if you're running on this environment. But anyways, this exercise is designed so that you don't need to have both of them at the same time. Okay, and at the end, allow interrupts, and that's the part what you need in order to some of them in order to basically set up the interrupt. For example, that 1 hertz, exactly the same as in here. Hmm. Hmm. Where was I? Ah. I was here. Good. I need more. Since that was just the how to set up the interrupt service routines, and then here's a full program that utilizes those. So basically we have the setup, pins, different pin modes, timers, and then we also have the interrupt service routine. Okay, this is different from that asserting a interrupt. So if you're having already software libraries that support interrupt, then you would actually say that a function is an interrupt service routine by basically by this method. You are defining it as an external interrupt with the attached interrupt routine. However, we don't have that one here, so we have to do it the hard way, but it works. So this is how you make the timer 0 interrupt service routine. ISR is a macro which makes this code to appear on the interrupt vector table. Okay. So practically what was in here? Wow. You need to set up the registers and then use this ISR routine to set that interrupt vector into the interrupt vector table. And then actually after that in this loop you can do whatever you want. We could actually try some of that code just for fun. Since we already have this fabulous Lahti device here, LED pins and then push buttons. Let me demonstrate how this works just by oops. Let me take the code out. I don't need the push button. I'll just make this LED to blink at rate, well, about 1 Hertz or so, or once a second. Code. I don't need that code anymore, since I need everything that is required to make. Okay, that 1 Hertz is just fine. On setup, I think, and port pin 13 was my output, and then I need timer 1 setup, or maybe I just copy everything and then just remove whatever is not needed. So that's the whole thing. Maybe that's easier that way. Okay, good. Okay, I think I didn't get everything from this one. Okay, yep. Storage variable and setup was missing. Right, so pin mode. We are using just pin 13. We are not using 2 kilohertz. Don't need that one, or 8 kilohertz. There. Okay. And then we don't need that timer 0 compare vector at all, and or timer 2 compare vector at all. Okay, digital write, we have here toggle, and we need toggle number 1 there. So now I have 1 Hertz thingy here, and now basically when I start this one to work, it should blink that LED at rate once per 2 seconds, since the interrupt comes on once per second. So basically the full cycle would be 2 seconds. Let's see, does it work? Initializing. Doesn't do anything. Oh, yes, it does. It just... okay. See the simulator time. Now the simulator time is actually slow, a little bit slower than the real time, I think. Yeah, it's built a little bit longer. So simulator runs slower than real time. Ha! Okay, I think we got something here. Let me stop the simulation. So after all that jargon, we started from timers generally, AVR time unit, internal structure. Okay, those are the registers around there which basically control this whole thing. Where it's used. Okay, ensure some functions are executed at fixed time intervals, like in here it's blinking the LED. Multitasking on real operating systems, that's fun fact. Yeah, it can be used. For example, now we could have a scheduler there running at 2 kilohertz, for example, and then switching from one task from to another on Arduino. Unfortunately, we don't have the real hardware, but we have a limited simulator. But it still has the simulator for the core, the processor core. So whatever you are having code for processor core or the registers and such, it simulates just perfectly. So if you buy this Arduino yourself on your own money, then you can use whatever library you can find from internet, and there's a huge selection on everything. So there is actually a separate library for timer and counter operations. But we did it the hardware way, or hard way, the old school, so to speak. It brings me fond memories. I'm sweating already. The AVR MCU, that was the example from the picture, and then there we have this total 9 registers, flag registers, a read-only register, and then we have these 8 registers, and if it's a 16-bit counters, all the data registers are 2 bytes long, lower and higher. Okay. And on the control register, every single bit matters. So if you want to try something else, for example, okay, we could actually try on that one, make this clock go 4 times faster. We could actually now null the CS10. That's something we could actually just check that it works that way. Okay, configuring, meaning that you are writing directly to the control registers, the count value register, then compare match register, so 15,624 ticks, clock ticks is the same as 1 second. And there's actually this can be calculated from the formula that is shown on this datasheet, or that nice example sheet. And the later one, Arduino timer interrupts, is the one with didn't have that funny extra feature showing some nasty stuff on the lower right corner. But actually that's the so I would say Teach Me Micro, they don't have much of the data security on their website. I will remove that link immediately after this class. So, and then let's go to this one here. okay, controlling these things. What you need to do on the setup, set 7 different registers. 7 different register values. And then you need to also state that, okay, the timer 1 compare a interrupt vector. This mask here actually relates to when to do the interrupt, and that bit must match also the interrupt service routine on the vector table here. Enable timer compare a input. There. Counter interrupt enable 1 a compare value. Good. So yeah, this is the interrupt service code, which is then saved into the interrupt service routine, interrupt vector table, the address of this routine, and then independent of what happens in loop, this will execute this code. As you can see, we have empty loop here, so anything that happens, or everything that happens in this program is on interrupt service routine. And there I also said that, okay, maybe we could try different prescaler just for fun. So I'll just comment the end of that one, which means, okay, which means that my prescaler is now 100, and maybe with some luck, if I start simulating, it may actually blink faster. Maybe. We'll see. Still initializing. Still initializing. It takes for a while. Yeah, nice blinks faster. Wow, that was a full session again. How about, before continuing, although the next session is quite short, how about having a 5-minute break to digest whatever I said? So 5-minute break continues at 15 and that'll be 18, something like that.